Good afternoon. Thank you very much for coming to my talk. As you know, I'm a historian, and this is the Center for Theoretical Physics. So the topic may be sort of unusual for what you are familiar with. But anyway, today I'm going to give you an introduction of a historical topic about a theoretical problems in physical science. And I think historians' mission is different from physicists, right? So we're not really care about who's right and who's wrong, but we really care about what happened in the past and then what lessons can we learn from the past. So
the microphone.
The microphone is just for the video. Yeah, it's not broadcasting microphone.
Oh, not broadcasting.
No. So yeah, I hope you have fun with this episode, with this story, and if you have any questions, comments, suggestions, please do not hesitate to let me know. So today I'm going to talk about a specific theoretical developments at the end of the 19th century and early 20th century, and that has to do with the creations of the German theoretical physicist Gustav Kirchhoff. So in 1882, Kirchhoff, at the time a professor at the University of Berlin, published a paper, Theorie der Lichtstrahlen. So it's on the theory of light rays, which is about actually about the diffractions of light. And this theory is interesting because it is sort of a classical work for light diffraction theory, but on the other hand, it has some severe problems. So, well, first of all, the theory, or at least an important part of the theory in Kirchhoff's paper, had to do with the light diffraction from the slit on the screen, which is a canonical scenario in diffraction. And the theory is based on the wave equations and a set of intuitive boundary conditions, which is that there's no fields in the shadow parts of the screen, and the fields in the opening aperture part of the screen is identical to the incident fields. Okay, in other words, the slits on the slit of the screen, the field is equal to the incident field. So based on this boundary condition, he could derive a diffraction integral, which is compatible to the result that the French engineer Huygens-Fresnel had discovered decades ago. And that was very good because Fresnel's result not only was accepted as as sort of the canonical wave theory of light, but also has some empirical confirmation. But then scientists soon discovered that Kirchhoff's theory had some problem. Well, the major problem was that his integral was inconsistent with his boundary condition. In other words, the diffraction integral coming out of Kirchhoff's theory cannot reproduce itself on the boundary that he's dealing with, namely on the screen and aperture. So in other words, this is an inconsistent theory because the result, the field result does not reproduce its boundary condition. However, even though this was shown by the late 1890s, this was shown to be inconsistent, but scientists still continue to use the theory. So in spite of the fact that they were shown that the theory was inconsistent and incorrect, but the scientists still continue to use it. So why? What's the reason for that continuations of the use of the theory in spite of the fact that it was incorrect? So does that mean to the scientists at the time, and also maybe for us, that a successful scientific theory does not have to be real? Okay, so this is a sort of more or less philosophical question. So I guess at the end of the story, I would like to present my reading of this episode, my interpretations of this episode, which may address that question. But what I want to raise your attention is that this episode, this story, may give us some opportunity to reflect on the success of an inconsistency. So in this kind of reflections, we have to pay attention to the balance between rigor and usefulness. So a theory can sometimes be very useful but not very rigorous, and the other way around. But in scientific practice, scientists were always struggling between rigor on the one side and usefulness on the other side. So I think this is a wonderful story to demonstrate that delicate balance between rigor and usefulness. And second, one way to strike a balance between that rigor and usefulness was to try to find the issues or conditions for idealization and approximation. Well, the empirical world is the empirical world. So when you try to study, approach the, or represent the empirical world with theory, that is always an approximation or idealization. The question is, what kind of idealization and approximation, and what are the conditions of approximation and idealization that scientists employed in order to legitimate themselves? Okay, so for that matter, I would like to introduce a notion at the end of the talk, which is the notions of theoretical platform. And this notion refers to the idea that when scientists are using theory to represent or to deal with nature, the empirical world, they actually write on some existing conceptual framework. And their theory may not be the same as the previous theory, but they inherited some kind of ideas or framework or structure from the previous theory. So that was what I refer to as the platform. So I will use that concept to have this discussion with the issue about the question whether the scientific theory needs to be real or not. Okay, so back to the story. So this is the standard canonical scenario for physicists working on optical diffractions in the 19th century. So basically, you have a light source, point source S, and you have a screen with the opening aperture over here. So and over this part, it's blocked. This part blocks the light, so we can say that there are two regions of shadows on this part, and light penetrates through the aperture and goes to the open space over here. So if you put a screen like a screen or projector or whatever surface over here, we can see the interference pattern over here, right? So this is a high school textbook physics, the Fresnel diffraction pattern, which we know. Okay, so well, of course, that kind of diffraction problem had been dealt with by physicists since the late 18th century, but the one who gave the most authoritative answer to that question or gave an authoritative theoretical treatment to that problem was the French engineer Augustin Jean Fresnel. So, and that was sort of, and he was dealing with the problem at the time during the regime transition between the Napoleon periods and the Restoration. So he was a graduate of the École Polytechnique, but did not have employment and stayed at home and tried to find something useful to study. And then he came to this diffraction problem. So to Fresnel, the diffraction problem could be dealt with in a way that the 17th century Dutch natural philosopher Christian Huygens proposed, namely this idea of Huygens principle. So basically, this is the same aperture and same light source, point light source, and this is P is the point of observation. So Fresnel's theory has some assumptions to begin with. First, light is an undulation or undulating wave in ether. So at the time, like most of the natural philosophers, he assumed that there's a permeating invisible media called ether that was responsible for the propagation of light, right? And light was sort of the agitation or perturbation disturbance of that material. So light was a wave-like phenomenon. So this, of course, was the sort of most, the final versions of the wave theory of light in the early 19th century. And moreover, how do we get the intensity of light at the point of observation? So to Fresnel, the intensity of light is just the sum of contributions from all the points on this wavefront. Okay, so when you have a point source over here and the wave just spread out like water ripples, and on this surface which touches upon the aperture, there's a wavefront originated from the source, right? And the light diffraction is just the sum of all the contributions from all these points on the wavefront. So that was Fresnel's theory. And this theory used, as I said, the so-called Huygens principle, which the Dutch natural philosophers Christian Huygens proposed about a century before that. Okay, so here's just to give you some idea of detailed calculations that Fresnel used to come up with his results of diffraction. So let's say this is the light source I, the point light source I, and this is the screen, the block AG, and suppose it goes to infinity, so this is semi-infinite screen. And this is the point of observation. And Fresnel's question is to calculate the light at this point, giving the source and the screen. So of course, the light over here should be should have two components, one directly coming from the instance from the light source, the other from diffraction, right? And the question is, how much contribution from the diffraction? So to Fresnel, we should use the Huygens principle, namely, we should consider the light intensity over here as the sum of all the contributions from the wavefront over here, right? So this is a wavefront emanating from the light source I, and at this point, this is the whole wavefront should be a sphere, but because this part is blocked by the screen, it doesn't count in the part of integral. Instead, the integral only goes from here to the infinity over here, right? So the actual intensity of light at the point of observation O is integral over all this part of the wavefront A, N, capital N, and N prime. Right? So if you carry out that integral by just detailed calculation, you can get the intensity of the light as the sum of these two integral forms. And they happen to be, well, not happen to be, they are exactly in the same form as the Fresnel integral that we now know today, which is the integral of the sinusoidal functions with the arguments, whose argument has a second order of the variable, right? So in this case, that's z. Okay, so that's Fresnel's integral. So this is a Fresnel's the theory of light diffraction. So notice that even though this is a wave theory of light, Fresnel did not assume any form of wave equation. Instead, he invoked this physical reasoning, like Huygens' principle, that for a wave emanating from the light source, we should deal with the whole wavefront and consider the contribution from all points or all effective points on the wavefront. Okay, but then you would wonder what happened if we incorporate this perspective on the wave equation? So that was exactly what the next scientists did in the mid-19th century, and that was George Stokes, the Cambridge mathematician, the famous tutor of tripods, who gave the tutorial to a lot of students at Cambridge passing through the tripods mathematical exam. So George Stokes was a leading expert in hydrodynamics and mechanics. So in 1849, he wrote a paper trying to deal with the problem of diffraction through more mechanical treatment. So in this paper, he treats light as a perturbation propagated in an elastic medium of ether, which was not so different from Fresnel's assumption. Okay, but then the novel step he introduced was to invoke the wave equation. So here he argued that from the mechanical properties of ether as an elastic solid, okay, not a liquid but solid, we should we should be able to write down the distortions of the ether, which is the wave, the light wave, as a this form of the dynamic equation. So you may wonder why he modeled ether as a solid, not a liquid, because, well, the simple answer is that because at the time people were already familiar with the polarizations of light and figure out that light has polarizations perpendicular to the directions of propagation, and for liquids, it's very difficult to imagine wave the propagations of transverse wave, right? But for solid, it was very straightforward to imagine that. So that was the reason why a lot of mid-19th century physicists assume ether to be a solid, not a liquid. But of course, you may encounter all kinds of problems, because how come this invisible, non-tangible material to be a solid? So that eventually led to sort of the demise of the ether theory. But that's another story. Okay, so this is the dynamic equations of the ether perturbations of light wave. This is sort of in the form of the wave equation, but to make this form more explicit, Stokes decomposed this distortion into two components, compression and rotation. So compression is curl-free and rotation is divergent-free. So these two components follow two sets of different equations, and both are exactly like the wave equation. Okay, so now we have the wave equation for ether, and the question is, how do you come up with the solution for the ether? So Stokes' solution was sort of complicated, so I would not like to, I will not try to explain the form of his solution. Instead, I will just highlight one result of his solution, which is the following. So consider this is a light source, a point source, and consider this is the imaginary infinite plane. Then there's no physical physical materials on this plane. This is just imaginary plane in space, right? So considering the form of solution in Stokes' equations, Stokes argued that if we want to find out the intensity of light at this point of observation, it can be expressed as the integral of a contribution from all these different differential volumes, and each contributions from each differential volume, d sigma, is in this form. Okay, so eventual light intensity on the point of observation would be the integral of this contribution over all this imaginary plane. And when he does that, and he really did that, he found that the results of the integral is exactly the wave that emanate from the source without any block. In other words, it's just a simple spherical wave. If you integrate over the entire imaginary plane. In other words, Stokes' solution to the wave equation is a consistent solution, because when you integrate over all the plane, you get the original results, right? So this sort of shows that Stokes' solution is consistent. But even that's the case, this still doesn't answer the question of about the condition when there is a block or there's an obstacle in the physical scenario, because this only deals with the source and the point of observation. So basically, it's a wave in the free space. Okay, so the first person to undertake the task of dealing with the, well, not the first person, but the Anyway, so the next person who undertook the task of dealing with the light diffractions over an obstacle was this German physicist Gustav Kirchhoff. So Kirchhoff was a famous theoretical physicist at the time, and this was a period when the German state universities were establishing chairs in theoretical physics, and Kirchhoff was sort of one of the leading professors of theoretical physics, and he was famous for his work in spectroscopy, in mechanics, in electrodynamics. But by the 1870s and 80s, he was already located at University of Berlin and was close to his age of retirement. So he spent more time teaching and trying to come up with textbooks for teaching. So this was a paper exactly written for the purpose of teaching, which was to give a synopsis and synthesis of the major elements of the wave diffraction theory of light. Okay, and this is the one that I talk about at the beginning of this talk. Okay, so in this paper, Kirchhoff tried to give a solution to the wave equation, but with the sort of smart manipulations of the boundary condition. So the key point for his way of coming up with that was to use the so-called Green's theorem in vector analysis. So I'll try to minimize this technicality of this, but just to highlight the important steps that he went through. So basically, you want to solve the wave equation with specified boundary conditions, but the idea to do that is to express the field at any point in the space in terms of field contribution from a closed surface, which can be interior or exterior to that point of observation. So let's consider the situation in which the point of observation is within that surface. Okay, so in that case, he considered this Green's theorem involving the surface integrals S over S and the volume integral equal to the volume integral over V, the volume encircled by that surface, right? And there are two functions over here to consider. One is the G, which is so-called Green's function. The other is phi, which is a wave function. Okay, and this rho phi rho v is the differential over the normal direction, namely is the gradients to the normal direction. Okay, so for these two functions, the light field phi should satisfy the wave equation. And then the other function g is up to his choice. So he chose a Green function in a way so that it could facilitate his solutions of the wave equation. So specifically, the Green's function that Kirchhoff chose was like this: R0 over this function f. R0 is a distance from the point of observation to the point of contribution, right? And this f is like Dirac delta's function, which means its argument, well, it's 0 when its argument is non-zero, right? Well, but when its argument is 0, it is like a peak, infinite peak. Okay, so now, so since this Green's function that has a singularity at the point of observation O, right? So when it's at O, R0 equal to 0, so that's a singularity. So strictly speaking, when we consider the Green's theorem, we should encircle this point of observation within the small volume and consider only the volume exterior to that small neighborhood, right? So more precisely, the Green's theorem should be written in this form, in which the small s and capital S refer to this exterior surface and the interior surface surrounding S. Very small, infinitesimal small surface surrounding O. And this V is the space between small s and capital S. Okay, and then now you have all the elements that you need to solve the wave equation. So consider G's behavior, Green's function's behavior. Green's functions satisfy the wave equation, except for at the point of singularity. And the phi also satisfy the wave equation. So if we take the second derivative, partial derivative of time over all this, and plug in and then get rid of the infinitesimal contributions of the surface integral around capital S, then we get this, right? Which is exactly the expression of the wave of the light intensity at the point of observation in terms of the surface integral over this surface, closed surface S. Okay, and this omega is the integrand, which involve the wave involve the wave phi and its first order spatial derivative. Okay, so in this expression, the light fields at O is the sum of all the contributions from all points on the surface S. And this is exactly the form that Huygens' principle gave. The only difference, and that's a major difference, is that this expression is not derived from any particular mechanical or physical consideration like Huygens did. Instead, it came from the wave equation. It was derived. Okay, so that was the situation when we have the surface circling or encompassing the point of observation. What about when the surface is outside the point of observation? Okay, so in this scenario, Kirchhoff argued that we can do the similar thing by considering three surfaces: this existing surface S and the small surface capital S surrounding the point of observation, and the infinite surface at infinite space, right? So if we consider all this, we can get the similar result, which is to express the point of the field at the point of observation in terms of the surface integral over S. And the only difference is that in this integral, all the point contributions on any point on the surface actually comes from the light intensity from the point source I inside the surface S. In other words, in Kirchhoff's expression over here, how do we get the field intensity over at the point of observation O? First, we consider the fields emanating from the point source I, and then calculate the point of the light intensity on all the points on S, and then we do the integral over all points on the S with respect to O, and then we get the result, which is what this says. Okay, so this can apply when this surface S is imaginary, a virtual surface, or when it's a physical surface that involves real obstacles, right? And it gets interesting when this surface or part of it involves the actual physical surface, which is exactly what Kirchhoff was trying to deal with here. So now, back to the standard scenario for diffraction. Again, you have a screen S, S0, and you have aperture A, and you have point light source I, and you have point of observation outside the screen. So consider this closed surface. This is exactly the surface S that Kirchhoff deals with here, right? So when you consider the surface integral over S2, S0, and A, here's something to consider. One is that the field contribution from the infinity is null because the Green's function has a 1 over r term, but this sort of decays over 1 over r cubed. So it decays more quickly than the, the Green's function decays more quickly than the contribution, the spatial contribution actually from the infinite part. So we can safely say that the contribution from S2 actually is 0. So we only need to consider the contribution from S0 and A. And then here comes important assumptions that Kirchhoff made in terms of the boundary condition. He say well, we have to pay attention to this, that over here on S0, there should be no instant field because that's a shadow, right? Because the instant field is blocked by this other sides of the screen. So when you are at the point of observation, you should see no instant fields on S0. So this on S0, phi should be 0. Spatial derivative of phi should also, rho phi rho n should also be 0. So that's one boundary condition Kirchhoff made. The other boundary condition, on the aperture A, Kirchhoff assumed that phi should be equal to the instant field, and rho phi rho n, namely the spatial derivative of the field with respect to the normal direction, should also be equal to its counterpart in instant fields. In other words, there's no contribution from S0, and for the contribution from A, it's just identical to the instant fields. Okay. So these are the important boundary conditions. So at S0, phi and its first order derivative equal to 0, and at the aperture A, phi and first order derivative equal to their counterpart for instant fields, right? As if there's no aperture, as if there's no screen at all, right? And now you have the boundary condition, you substitute the boundary condition into the form over here, right? Into the form over here, and you get this, right? So again, I don't want to go to the details of the form, but this is just how the result that after he substitutes the boundary conditions into the integral, and he get this. And this, of course, is a wave. And when you have a sinusoidal harmonic wave, it has a sine component, cosine component. So you can calculate its intensity, and you get this, which is the sum of two components, right? And this sum of two components are exactly like Fresnel's integral, which I just mentioned a few slides ago. So in other words, Kirchhoff integral like this could reproduce Fresnel's results, right? And that was very good because Fresnel's results was not only satisfactory to the physicists in the 19th century, but also conform to Fresnel's own empirical experimental data. So that means this result has some kind of empirical evidence or empirical validation. That's very good. And moreover, this result were not based on any like physical, mechanical considerations of the mechanisms of wavefront. Instead, it came exactly from the wave equation that Kirchhoff derived using Green's theorem. So it did not rely on any particular physical assumption, right? So, so in other words, this enjoyed the complete success as a complete and empirical adequate theory, right? So this is very good. But then the happy story did not last long because a few years later, in 1892, French mathematician Henri Poincaré wrote a book. In part of the book, he dealt with the light diffraction, and in that part, he had a challenge on Kirchhoff theory. So this Théorie mathématique de la lumière was not a paper, it was a textbook. So just like Kirchhoff, Poincaré at the time was teaching at university, so he was very concerned with forming textbooks for students. So this was a book he composed for teaching students physics of light. But at the time, people were much more willing to incorporate original research results in textbook than today. So anyways, in that book, he had a discussions on Kirchhoff theory, and he found, and in his discussion, he argued that he demonstrated Kirchhoff theory was not consistent. It was incorrect. It was not a consistent theory. How so? He argued that Kirchhoff theory was not consistent because his integral, his light diffraction field, could not reproduce its boundary condition. It was not consistent with its boundary condition, right? So in other words, in Kirchhoff diffraction fields, phi and rho n do not vanish on the shadow region, and they do not equal to the incident fields on the aperture. So this means that Kirchhoff assumed a set of boundary conditions, used the boundary condition to solve the wave equation, get the diffraction fields as a form of integral. But when he goes back to check whether that diffraction fields can reproduce the boundary condition on the boundary, he cannot. Therefore, there's a problem. Kirchhoff theory was inconsistent, was incorrect. Okay, so now I just give you some sort of cartoon versions of how Poincaré derived the inconsistency of Kirchhoff theory, but he was very brief. So my research collaborator and I were trying very hard to reconstruct Poincaré's reasoning by consulting some other later textbook. But anyway, this is we believe the sort of the right picture that he went through in order to derive that result. So consider again as light source M, point source, and point of observation P, and a screen. Here the screen is distorted to a weird form, but anyway, you know this is a screen with an aperture A, right? And the screen has two sides. One side, the side B, is facing the point source. The other side, C, is exterior to the point source. So this is useful to keep in mind. And suppose, again, we have instant fields phi I, which come directly from the point source without any obstruction, without any obstacle. And we have diffractive field phi R, which is a result when we place this obstacle over here, right? So if we remove this, you get phi I. But if you place this back, you get phi R. And with the point source, you get phi R. And denote this integral in this form, okay, and where GP is a Green's function with respect to the singularity at the point of observation. So now, according to Kirchhoff's boundary condition, his main results imply that the diffractive fields at the point of observation has only the contribution from the aperture A, and in this contribution, the fields inside is assumed to be the incident fields, right? So this is exactly the result, the major results of Kirchhoff theory. And this implies something interesting. So from Green's theorem, the actual diffractive fields at the point of observation should come from three different surfaces. The small surface SM, the surface B, and the surface C, right? Because they are the only surfaces in the whole space. And we know that the contribution from the surface C should be equal to 0 according to Kirchhoff's boundary condition, because remember, Kirchhoff assumed that the shadow part of the screen should have 0 fields, right? So the C should go out. So only contribution from SM and B. And moreover, from Kirchhoff's main result over here, the contribution from here and here should in the same form as the contribution when the fields inside the bracket is the incident field. Okay, so we should replace phi R with phi I over here. So this is the main. This is one interesting result of Poincaré's derivation. Let's give the equation star. Name the equation star. And moreover, let's consider another scenario which we have exactly the same surfaces, B, C, and the point source surrounding the sphere surrounding the point source Sm. But now, instead of considering the space, now we consider a point L, which is in the obstacle, right, between B and C. And that's form the Green's function with the singularity at L, okay, GL. So for that Green's function, we can confidently write that this integral should be equal to 0 according to Green's theorem. Why? Because L is inside L is outside this gray area, and this integral deal with the spatial functions in the gray area. So that means in the gray area there's no singularity because GL is out of the gray area. So according to the Green theorem, this integral should be equal to 0. And it should apply both to the incident fields phi I and the diffractive fields phi R, right? So these are the natural results of Green theorem. And then from Kirchhoff's boundary condition, as we saw in the last page, and consider this. And we also know that according to Kirchhoff's boundary condition, the diffractive fields phi R should vanish on C over here. So that means for this equation, the C part should go out. We only keep the Fm and B part as the domains of integral, and moreover, according to the condition star, we should replace phi R with phi I. So that gives us this, right? So Kirchhoff's boundary condition gives us equation 3. And now compare equation 3 with equation 1. They are exactly the same except that their domains of integrals are different. So this one has 3 surfaces, Sm, B, C. This one has 2, right? And both are 0. So that means this integral or integral contribution from surface C should be equal to 0. But this has a severe problem because in this integral, the integrand does not have any components in phi R in the diffractive field. It only has a contribution from incident fields, right? But you basically cannot imagine any relationship between the incident fields and the surface over here, because incident fields is a field where you have nothing, just the point source. So it should be arbitrary. Well, not arbitrary, but the incident field should be independent of the surface C over here. And you can create any arbitrary surface C that satisfy the condition, that satisfy this, but it's not possible to say that this is satisfied in general. Therefore, you have a problem. When you argue that this is hold in general, you're actually saying that you have a contradiction, and Kirchhoff theory is in contradiction. Okay, so that's Poincaré's demonstrations of Kirchhoff theory's error. Okay, so then Poincaré showed in 1892 that Kirchhoff theory was inconsistent because his diffractive field could not reproduce his boundary condition. And then some scientists began to ask what could be a consistent theory of diffraction. In other words, how can we come up with a consistent solution to the diffraction problem? Well, 2 major scientists contributed to that effort. Lord Rayleigh, the second directors of Cavendish Laboratory at Cambridge University, and Arnold Sommerfeld, another renowned but younger theoretical physicist in Germany, and long-established professor at University of Munich. But just for the sake of discussion, let's focus on the Sommerfeld's contribution to the consistent solutions of the Kirchhoff problem. So for Sommerfeld, the problem, of course, is to try to find out the set of boundary conditions, or to try to find out the solutions. To try to find out the set of boundary conditions that can produce consistent solutions, and so that the solutions can reproduce the boundary conditions. So how to do that? Well, he found that it was hard to do it in general, but it could be done in a particular scenario. So, which is this? Just suppose that the screen is infinite, right? So going to infinity on one hand, the other infinity on the other hand, and it's flat. So this is just two-dimensional flat screen, and with the aperture over here. So the key to come up with the consistent boundary conditions and the solution is to come up with different Green's function. So remember, in Kirchhoff's solution, his Green's function is R over, well, he used the delta function, but if we're in the frequency domain, so it should be R over e to the IKR, right? But to Sommerfeld's, this scenario gives us an opportunity to come up with more symmetric Green's function, which has certain advantages. So for this scenario, he argued that we can consider two Green's functions, G1 and G2. And these two Green's functions has some advantages because G1 is 0 on the boundaries S and A because of the symmetry, right? And G2's spatial derivative over N is zero on the boundaries S and A. Okay, so these two Green's functions have the advantages because it has special properties on the boundaries S and A. So one vanishes and one's derivative vanishes on the two boundaries. And why are they advantages? Because, well, first of all, which are they? What form are they? Well, because here Sommerfeld took advantage of the symmetric form of the boundary condition and considered 2 points, right? So this is the point of light source, and this is the point of observation, and this is the image of the point point source. So P prime light source, P image, and O is the point of observation. So GI is just the R over E to the IKR minus R prime over E to the IKR prime. R is the distance between P and Q. R prime, distance between P prime and Q. And G2 is just plus of these two terms, right? So when we have these two forms of Green's functions, this guy vanishes on surface S and A. The spatial derivative of this guy along the normal direction vanishes on surface S and A. So what does that mean? That means when we use GI, if we incorporate GI into the solution, we only need to specify the boundary condition phi on the surface A and S, not its first order derivative, right? But when we incorporate G2, we only need to specify the first order derivative, not the field itself. So in other words, using these two Green's functions, we don't have to specify phi and rho phi rho n at the same time on the surface. We can specify either phi or rho phi rho n on the surface. So this is a great advantage. And why is that a great advantage? Because this made the conditions of the this make it possible to meet the consistency conditions of the solutions of the differential equation. So here are the two forms of Sommerfeld's solution. So one evoke the Green's function GI or G1. The other evoke the Sommerfeld's Green's function G2. Right? And these two solutions are consistent with respect to their boundary condition because if you check, you can find this guy vanishes on the surface S and A, and this guy's spatial derivative over N vanishes on the S and A, right? So they are consistent with their boundary conditions. And retrospectively, we would say that this is a reasonable move because for the second order differential equation of the wave equation type, it's like elliptical differential equation, second order differential equation. Specifying the boundary conditions and the spatial derivative, specifying the field and spatial derivative, it's over specification, it's over determination, right? For the second order elliptical wave equation, we only specify the field or its first order spatial derivative. That's the complete specification. But if we want to specify both, it's over determination. It's bound to have some technical mathematical problems. So in other words, Sommerfeld's solutions sort of solve these problems of inconsistency for the second order elliptical wave differential equation, partial differential equation. So as I said, they are consistent with their boundary conditions, and the Kirchhoff solution is the average of the two Sommerfeld solutions. Okay. But now, here comes the puzzle. So Sommerfeld came up with these solutions around 1896. So this was sort of already known knowledge or given knowledge to mathematical theoretical physicists at the time. But in spite of Sommerfeld's solutions, scientists still continue to use the Kirchhoff solution, not the Sommerfeld solution, right? So in other words, even though scientists were aware that Kirchhoff solutions were inconsistent, they were still not very, they still continue to use that. They didn't give up. They didn't use the consistent solution, right? So then you would ask the question, why was the theory not abandoned, right? So one reason, of course, was that the Kirchhoff result was consistent to empirical evidence. So this is just one set of data produced much later, around 1950s and 60s. So some experimental physicists conducted the microwave diffraction experiment and did some measurement and found that Kirchhoff formula was actually quite a nice fit with the experimental data at microwave range. And of course, it goes without saying that as early as the early 19th century, Fresnel's data already had a good fit with Kirchhoff diffraction integral, right? So empirically, it seems that Kirchhoff diffraction formula went quite well, or quite satisfactory. So empirical adequacy was one important reason, I believe, that make the resilience of Kirchhoff theory. And another thing to consider is that from the early 20th century on, some scientists were trying to give reinterpretations of Kirchhoff formula. So that kind of work started with the late 19th century, and then continued to the early 20th century by two individuals. Antonio Maggie, who was a student of Kirchhoff in Berlin, but later on went back to Italy, became a professor there. And Albert Rubinowicz, he was a student, he was Polish, but the students of Sommerfeld. So both express Kirchhoff diffraction integral, not in terms of the surface integral over the aperture, but in terms of the instant field plus a line integral around the edge of the aperture. Okay, so this is a different expression, right? Well, you may say that the mathematics is mathematics, it's just a different expression, the result is the same. What's the big deal? But this expression can induce us to think about Kirchhoff result differently, because this expression may give us a hint that, well, the contribution, we may consider contribution not from all point on the aperture, but from all point on the edge of the aperture. So this gave us the possibility of revoking, let's say, Thomas Young's theory at the very early 19th century, in which only the edge of diffraction matters, right? So remember, the major difference between Young's diffraction theory and Fresnel's theory is that Young only considered the contribution from the two edges of the aperture, but Fresnel considered the whole contribution from the whole surface of the aperture. But now we have the line integral over the rim of the apertures, which seem to suggest that maybe there's some grains of truth in Young's physical theory. But this is just the opening of that new direction. So further later, around the 1960s, two other physicists came up with a more consistent theory for that matter. So they were Eric Marchand and Emil Wolf. So one was, I believe Marchand was working at the University of Rochester, upstate New York, and Wolf was a physicist at Polaroid, and both were students of Max Born, the German Jewish physicist, one of the contributors of the quantum mechanics. But anyway, so Marchand and Wolf in 1966 gave this formulation about the Kirchhoff diffraction theory. So they argue that, well, Kirchhoff's boundary condition could not produce his diffraction formula, but how about if we gave a different set of boundary condition? Then we may be able to produce Kirchhoff's formula, right? So this is the boundary condition that Mill and Marchand and Wolf came up with. So in this boundary condition, what happens on the surface, like the aperture and the screen, is more complicated than what Kirchhoff specified. So you can say that, well, this epsilon is kind of a delta function. So you may say that this is identical to Kirchhoff's boundary condition. Let's say if xy is outside the shadow region, is in the aperture, then this is instant field. But if it's outside, if it's inside the shadow or out of the aperture, this epsilon is 0, so this term is 0. So this corresponds exactly to Kirchhoff's boundary condition, namely, the field vanishes in the shadow, and the field is identical to the instant fields in the aperture. But this is the additional term, which makes the boundary more interesting, right? So in this term, this term actually is in the form of the line integral over the rim of the aperture. So this actually says that, well, if we consider what really happens on the surface, on the screen and aperture, it should contain not only the direct, geometrical optics contribution as Kirchhoff imagined, but also this diffraction contribution from the edges of the aperture. In other words, according to this new boundary condition, the shadow of the shadow part of the screen the field on the shadow part of the screen does not vanish, right? Because it has this contribution from the edges, right? So some diffracted light leak onto the shadow part of the surface, so it's not 0. And on the other hand, the aperture part of the surface does not have only the instant fields. So that's come back to your question, right? So the aperture part of the surface of the boundary, in addition to the instant fields, has this diffraction field coming from the edges, right? So this is a new boundary condition that the two scientists proposed. They argue that given this boundary condition, they could produce Kirchhoff formula, right? And Kirchhoff formula can converge to this boundary condition on the surface of aperture, on the surface of screen. Okay, so we can say that by 1966, these two scientists eventually gave a sort of more complete formulation for making the Kirchhoff theory consistent. Okay, so what lesson can we learn from this? Well, as I said, Marchand and Wolf's boundary condition is Kirchhoff's boundary condition plus the contribution from the edges of the aperture. And Marchand and Wolf's boundary condition is consistent with Kirchhoff's diffraction formula. I said that too. In other words, Kirchhoff's formula is a solution of the wave equation and Marchand-Wolf boundary condition. So, in other words, Kirchhoff's solution is not the results of the wave equations and Kirchhoff's own boundary condition, but this new, more complicated boundary condition. Okay. So that's the sort of the synopsis of the story. So now, how can we make of this story? Well, so around about a few years ago, two philosophers of science gave some interesting discussions on these episodes, and these philosophers were Juha Mathi and Peter Vickers, and they asked the question whether Kirchhoff theory was a miracle was a miraculous success, whether the success of the theory was just an accident, just happened to be a miracle. Well, so they argue, Stassi and Vicker argue that the story of Kirchhoff theory actually challenged the major thesis of a quite powerful philosophy of science, which is called the structural realism. So according to structural realism, even though scientific theory went through major changes over periods of time, they retain some real structures of they retain some structural features which correspond to the structure of reality, so that even though the non-structural part changed, but still that structural part remained the same. So this is sort of a belief in the reality of scientific theory. So even though, let's say, Kirchhoff theory was, for example, the diffraction theory was incorrect and there's no ether as we believe today, but we believe that ether may not be the essential part of the theory. So even though we don't believe in ether anymore, but the wave equation, the boundary conditions still give us, still capture the essential part of the reality. So the reality of the scientific theory does not lie in any particular physical, mechanical hypothesis, but rather lie in the structural features, like the mathematical configurations, like the mathematical framework. So that's sort of the very crude summary of the thesis for structural realism. But here, Kirchhoff theory posed a problem, right? Because his theory was neither consistent nor empirically correct. Of course, when I say his theory is not empirically correct, it doesn't mean that his formula does not have empirical evidence. It means that his boundary condition could not be reproduced by his formula, right? So if you say that Kirchhoff theory can believe to capture some structural features of reality, you run through a problem because that theory was not even consistent itself, right? It has a problematic structure. But however, his formula enjoyed empirical success. So what can we say? Vicker and Sassi said, maybe that means theory is not a mapping of structural features of reality, right? So maybe when we talk about the empirical success of the theory, it doesn't have to map some real features, some actual structural features of reality. But if it's not, then how can we believe in the validity of the theory in addition to its empirical success? So to philosophers like Vickers and Sassi, maybe there's nothing further to the empirical success. Maybe Kirchhoff theory was successful empirically because he was lucky, or it was a miracle, right? But so that was basically a challenge to this structural realism that Sassi and Vickers used to use the Kirchhoff story for. Well, here I would like to have a slightly different interpretation. I would say that maybe we should look at the story in a different angle. Well, of course, yes, I agree that Kirchhoff theory was not consistent because his formula could not produce his boundary condition, and he used the boundary condition to derive the formula. That was weird. That was inconsistent. But I would say that Kirchhoff's boundary condition, it may not be consistent, but it aligned with some existing theoretical framework, and that was Fresnel's platform. So when I say platform, I don't mean exactly the same formulations or theoretical model, but I mean the sort of same conceptual scheme. So Fresnel's assumptions, what underlies Fresnel's assumption is that the fields on the aperture, the contributions of the field coming from is coming from the contribution from all the points on the aperture, right? And the fields on the aperture is identical to the diffractive fields on the aperture is identical to the incident fields on the aperture. So these are the essential features of Fresnel's theory, and that is continued through Kirchhoff theory, right? So in that regard, Kirchhoff formula had a similar structural features to Fresnel's. And we also noticed that no matter it's Sommerfeld theory formula or Kirchhoff formula, they are numerically very close to each other at small angles from the aperture axis. So in other words, I believe that the Kirchhoff theory actually operates at some structural level not very different from the Fresnel framework, even though he used the wave theory and he used this fancy mathematical apparatus of Green's theorem, etc. But still, at the sort of basic theoretical operative level, it's not very different from the Fresnel framework. Okay, so Kirchhoff theory did not go far away from Fresnel's. And we know that Fresnel's theory enjoyed quite empirical success by the early 19th century. So it should not be a surprise that Kirchhoff theory enjoyed quite empirical success for the late 19th and 20th century. The wave equation, so what Kirchhoff did was to reformulate the theories to make it a wave equation based, but the basis was still the Fresnel platform. So this was what I want to argue. In other words, I believe that the story of Kirchhoff theory actually shows the robustness of the Fresnel platform, not the contradiction to the thesis of structural realism. Even though I personally do not have a philosophical stance against or for structural realism. Okay, so here's another small example to show you the resilience of the Fresnel platform. So these are the interferometers that Albert Michelson used in the early 20th century to do the astronomical observation. And you may know that Michelson was one of the two experimenters to do this interference experiment that gave trouble to the existence of ether, eventually leading to Einstein's theory of relativity. But anyway, so in his interferometers, he still used the very crude, rudimentary Fresnel approach to calculate the field or to estimate the field, the light fields. So he used the interference pattern to measure angular width of stars, and the way he calculated empirical interference patterns was still to sum the ray contributions from the sources at different points of the aperture. So this is pretty much a Fresnelian approach. So even though we're already in the early 20th century, almost a century past, scientists were still operating on the Fresnelian framework, in spite of all this theoretical changes from the wave equation to Maxwellian theory and etc., etc. So this gives you another angle about the robustness of the Fresnelian platform. So to conclude, this story is about the mathematical controversy in the wave theory of electromagnetics, in the wave theory of the light, electricity, and magnetism. And it shows the resilience of Kirchhoff's inconsistent theory of diffraction. I don't believe that this is a story about a miracle in scientific theory. I believe this is a theory about the resilience of an existing theoretical platform. Thank you very much.